Okay, should we get it started? Good morning, and welcome. We have Ed question reader, Jason. Thanks very much. He's here. He's going to grab his mic and shout out if you guys want to type anything in the classes. But again, no pressure. It's kind of up to Jason if he wants to paraphrase or whatever. And this, I've still got some volunteer spots left if you're interested. Late November and getting into December. Getting towards the end, definitely deep into the second half of this semester now. I wanted to start actually with the Ed discussion question that came in at the end of last time, which I didn't really answer properly, I think, because I didn't understand it at first. But the question was, remember this whole learning catalytics question? I pushed the box and all this stuff, and we were comparing two situations. The initial situation, just before I started pushing the box, to the final situation, just after I started pushing the box. The question was, why is W not 0 if the initial situation is before the box is pushed? So I get it now. Remember that the change in energy is defined, delta E is final minus initial. So what your textbook has done is a little confusing, but it's a repeated theme, which actually comes back when it gets into the thermodynamics chapters. But she rearranges this to be initial plus delta equals final. And that's exactly what that equation is showing there. So the change in energy coming from an outside force being applied to the system is the work. So the structure of this equation, it's the initial energy before I pushed it, plus the change in energy, which was the pushing, equals the final energy. So you stick the W over on the left-hand side of the equal sign, but that doesn't mean it's an initial thing. It's the delta. Okay. A little confusing. Hopefully that answers last day's question a little better, now that I understand the question. Also, we kind of left this without doing it. I thought maybe we'd do this. Again, this kind of finishes up stuff. We're not into collisions yet. I want to talk about collisions today, but let's just finish up this work done by friction thing. A small box of mass M is 10 kilograms. It's released from rest at an initial height of 2 meters on a frictionless incline. They don't tell you what the angle is there, but they do tell you how high up it is. So I think this is an energy question. At the bottom of the ramp, it encounters a rough surface, which I think is horizontal there, with a length D equals 1 meter, and mu k is 2.50 times 10 to the minus 1, meaning it's 0.25, a quarter. And then it goes on a frictionless circular rise. At what height hf does it stop? So you cannot do this question with kinematics, because you don't know any of the angles, and the circular thing is not even constant acceleration. So this is a really a chapter 7 problem that you have to work out using energy. So, but we can start off, sketch and translate by kind of listing our knowns. 10 kilograms, H initial is 2 meters. We need to find H final. And the distance on maybe this friction is the 1 meter. That's going to be important. And mu sub k is 0.25. Okay. So I'm going to define the system here is the box plus the earth and plus the surface. So, and by that what I mean is that when we include the earth, that we're going to include the gravitational potential energy, mgh. And when we include the surface, we're going to, I guess on the right-hand side of the equal sign, put the delta U internal as being the absolute value of the friction force times the distance. So U, delta U internal will be plus FKD, will be, it'll be kind of generated and left as like heat afterwards as this thing slides across here on the horizontal slide. I don't know, it's sliding, so I'll call it a slide. Okay, so the K initial plus UG initial plus external work equals K final plus UG final plus delta U internal. That's our conservation of energy equation. We've got the external work, which is going to be 0, I guess. We can draw our force, or our little, what are they called? Energy bar charts. So it starts from rest. So let's just, maybe with red here, well, this is 0 plus something. I'll keep it blue, I guess. It starts at some initial height. There's no external work done. So no external work done. So some of it's going to go to the UG final, and some of it is going to go to the U internal. So both of these bars are they're positive, and they're a little less than this UG initial. And everything else is 0. It's actually starts from rest, ends at rest, and no external work. So so I guess I'm going to assume, the box starts and stops at rest. So I'm just trying to figure out which of the terms are 0 and then solve it all out. So I've got 0 initial kinetic energy plus mghi plus 0 external work equals 0 final kinetic energy plus mgh final plus F sub k times d. And it's a horizontal surface. So you've got normal forces up, Fk is backwards, mg is down. The sum of all the forces in the y direction equals 0 because it doesn't have any y acceleration, right? So that means that normal force minus mg equals 0, so the normal force equals mg. So Fk is going to be normal force times mu sub k. It's going to be mu sub k times m times g. So our energy equation becomes mghi equals mgh final plus mu sub k times m times g times d. And now we'll use red to just divide all the terms by m. Turns out the mass of the box doesn't matter, which is good. And we get H initial equals H final. Actually, I'm going to cross out the G's as well. You can divide both sides by G and M plus mu sub K times D. Solve for H final is H initial minus mu sub K times D. So it's 2 meters minus 0.25 times 1. H final is equal to 1.75 meters. Okay. Not quite as high as the initial, which makes sense. Shouldn't go any higher than the original, because you've lost a little energy as you've slid across the rough surface. Good for discussion. Who's good with that? I think I want to get on to collision stuff next. We're going to talk about elastic, inelastic collisions. Start with a learning catalytics question, shall we? Looks like this. A firecracker explodes in midair and suddenly breaks up into many fragments. Which of the following statements are true regarding conditions immediately before and immediately after the explosion? So I think we talked about this before, actually, in chapter 6, that collisions and explosions share this thing in common. So there's Roman numeral I. First one is the total momentum of the fragments is equal to the original momentum of the firecracker. So you've got firecracker just before the explosion and fragments just after the explosion. Roman numeral 2 says the total kinetic energy of the fragments is equal to the original kinetic energy of the firecracker. So when the explosion happens. So they're either both false, one of them's true, or both true. So once you had a chance to think about that a little, I'd like you to find a neighbor, pair up, convince your neighbor. Make sure you're both voting the same way. I'll give you a minute to talk about that. Got the chapter? Yeah. All the numbered ones, yeah. Okay. Somebody was saying that they like the number questions better than the conceptual questions. Well, there's going to be some conceptual questions on the term test. So let's see what the survey says on this. Please click in and answer. Seeing 330 of you. I've done that. 337. Going once, going twice. Stop. So, statement 1. So this is a really important concept, which is that momentum is always conserved in a collision or an explosion. Reason being that the change in momentum is some external force multiplied times delta t. And so delta t in the case of a collision or explosion is extremely small. So there can't be very much change in the momentum of the system. This is called the impulse approximation, which is if you've got a collision or an explosion, you can't change the momentum much. So the thing to remember here is, I'll just write it down because it's important. So it's B, just this. Certainly there's tons more kinetic energy after it explodes than just before, and that is because you have chemical energy that's stored in the gunpowder, which is converted into kinetic energy when the thing explodes. That's what an explosion is. It's a creation of a bunch of kinetic energy. But it can't change the momentum. So during a collision or explosion, the external impulse can be neglected. This is what's called the impulse approximation. So we say that P initial, which is a vector, is equal to P final. There's no external impulse. But I will just say that the chemical energy of the gunpowder is converted, this is what kills you, to kinetic energy of the fragments. Might be a little hard to picture that, but what I always picture is you have two, if it breaks into two fragments, So maybe if it was sitting perfectly still, 0 momentum, 0 kinetic energy, then it can break into 2 fragments that are going very fast in opposite directions. So they both contain positive kinetic energy, and they could kill 2 people, I guess, on either side, but their momentum sums to be 0. Because one's a positive momentum, one's a negative momentum. Okay? Okay. So, we're on 7.7. Collisions. Collision is a process that occurs when 2 or more objects are in direct contact for a short time interval. So momentum is conserved. Kinetic energy is not necessarily. So with data, we can determine the amount of kinetic energy that is either converted into internal energy or maybe converted out of chemical energy or something. But you can't predict ahead of time how the kinetic energy will change. Somebody usually just tells you what the final kinetic energies are. And I guess if you have lots of experiments and they're the exact same thing, you can make these predictions, but these are going to be empirical predictions. In collisions where a deformation of the system occurs, then that's converting kinetic energy into some sort of internal energy. But, as we just said, the momentum at least is conserved all the time, has to be. So, in terms of vocabulary, she divides this into 3, elastic, inelastic, and totally inelastic. So, elastic means that both the momentum is conserved and the kinetic energy. Inelastic means that the momentum is conserved, but the kinetic energy is less just after than before. And I guess in real life, all collisions are inelastic. And elastic collisions are kind of like a ideal situation in which no energy is lost somehow. And then there's something called totally inelastic collisions, and that's where they stick together. So might as well let's just show them here. It's octoplate. Yeah, so what you can do is set up their collision carts. So that's totally inelastic when they have Velcro, and when they have the how do you do it? Yeah, there we go. So when they have the magnetic repulsion, you can get something that's pretty close to an elastic collision, where they just transfer. So somehow the momentum, since they have the same mass, actually, the momentum is conserved, same before and after. And the kinetic energy is conserved. It just transfers all its kinetic energy from one to the other. That's what happens when you have 2 equal mass objects and one of them's at rest. That turns out to be how you do it. Then a totally inelastic collision, you switch this around so that there's now Velcro, making them sticky. And then what happens is, that didn't work. I'm always turning the wrong one, I guess. There we go. You have to turn the left one. Okay. There we go. So then what happens is that the momentum is conserved, so now the 2 mass conglomerate is traveling half as fast as the original, but the kinetic energy is decreased. So somehow this Velcro in here has absorbed a bunch of kinetic energy, and now it has internal energy. That's the purpose of the Velcro. So it's called totally inelastic. Okay.
Hey, Professor, we got a question.
Yes, Jason.
There's some confusion on the term impulse. Can you re-explain what it is?
Impulse is 2 things, actually. It's a great question. One is that it's the change in momentum. That's sort of how I think about it in my head. But the way you calculate impulse is it's equal to F delta T. So it's the external force on your system multiplied times the time interval. And somehow those turn out to be the same thing. So F delta T, if either the force is small or delta T is small, then the impulse kind of goes away. So it's kind of weird. Chapter 6 was all about momentum and impulse, and you've got initial momentum plus the impulse is the final momentum. Chapter 7 is all about energy in a system, and work is this change in energy. So you've got the initial energy plus the work is the final energy. And the work is, I guess, force times distance, and impulse is force times time. That's a great question. Okay, yeah, we're going to do a whole bunch of learning catalytics now. It's 11:30, so we got some time. These ones, someone was asking for numerical, so I think these are all going to be numerical. They look kind of conceptual, but I'm leaving some space here because I think you have to work this stuff out. First question. Here it is. Is this an elastic, inelastic, or totally inelastic? Or the collision is not physically possible? So I'm getting confused. Remember, elastic means it's the same kinetic energy before and after. No loss in kinetic energy. Inelastic, so B would be that some kinetic energy is lost, but they're not stuck together. They're not traveling at the same final velocity. And totally inelastic means they end up traveling at the same velocity. So that's a hint. I could write that down. Well, yeah, that's a great question. Yeah. Are they stuck together? It was a great question. I just heard shouted out. So I said in a totally inelastic collision like Velcro, they end up stuck together. Another way of putting that is that they end up with the same final velocity. But I still want you to check the momenta. Makes sense? I think it could be C or D. Okay, guys, I see a lot of you have clicked in. Should we look at what survey says? And then I'll check the momenta. Going once, going twice. Yeah, we're going to do 3 questions just like this, but with different numbers. You're totally right. With C, they end up with the same final velocity. So in that sense, they're kind of stuck together. That's how it would really look. But I do think it's worth it just to check the momenta quickly. So just before, and then I'll give you another question here. P initial is equal to 2 times 3 plus 8 times 1.5, which is 6 plus 12. So P initial is plus 18 kilograms meters per second. And then after, P final is equal to 2 times 1.8 plus 8 times 1.8, which is, what is that, 3.6 plus 14.4. So I got plus 18. Good. I guess I was just a little worried that it could be D. But yeah, so P final equals P initial, so it's okay. So I always like to conserve momentum. So, and they're kind of stuck together. Okay, let's do another one. Got 2 more. Same exact thing, but different numbers. Different masses and different final thing. You guys get it? Basically, it could be C again, and that's fine. But let's check. Don't forget to check your momentum, because in all collisions, momentum should be the same before and after. If it's not, then it's not a real collision. Okay. Give me 1 minute. Give me a check. Tell your neighbor what you got. Yeah, is there any questions from the discussion board? Just.
Someone asked that during explosions we can neglect impulse because the time is very small. What about the force? Is it big or small?
Well, that's a great question. So the external force on, like, if you throw a firecracker up in the air and then it explodes, which you probably shouldn't do it while you're holding it, the external force is the force of gravity on the firecracker. So it's fairly small as well. There's internal forces on the fragments, which are large, but those are not going to provide any impulse, because impulse is always from an external force. And then, I guess, during a collision, sometimes the external force is the friction of the road with the cars. Or with the road. Yeah, okay. So you've had time. Going once, going twice, and stop. And what was really interesting from my perspective is that I was watching at first, C was like by far the most popular answer because it's the obvious answer. And then people heard me saying, let's check momentum, and then D gradually grew and grew and grew up to 69%. So let's just see here. But I think, but you got it, right? So before, I've got P initial. It's going to be 9 times 2.1 minus 3 times 0.6, because remember, momentum is a vector, so the plus or minus determines the direction, and these are going opposite directions. So I've got 18.9, I think, minus 1.8. So I got plus 17.1 kilograms meters per second. And then after, P final is 9 times 1.5 plus, they're going same velocity now, same direction, plus 3 times 1.5. And I got plus 18 kilograms meters per second. So it's not it's close, but it's not close enough. Not the same. Okay, so this is not possible. Last one. This time they're not going the same velocity. Okay, so I'm going to leave it on, but I just wanted to point out, first step I usually do with these things is check the momentum conservation. This turns out to be okay. So I think this is a physically possible situation, so I can rule out D there. So now, and I also know it's not totally inelastic because they're not traveling at the same velocity at the end. So now I just need to figure out whether or not kinetic energy was conserved or some of it was lost. I guess that's another thing that could happen is you could have more kinetic energy at the end than at the beginning. So it could still be D, I guess. But let's just check it out. So let's check kinetic energy, which, by the way, is always positive. So it's a different equation, and it turns out to be a lot different. So before, K initial is equal to, it's 1/2 mv squared, right? So 1/2 times 4 times 1.8 squared plus, doesn't matter which direction they're going, they all have positive kinetic energy, times 6 times 0.2 squared. So I plugged that into my calculator, I got 6.48 plus 0.12 is 6.6 joules. So that's the initial kinetic energy of these two things. Then you can do after. Okay, final equals, actually, you know what? I want to see if you guys did it. Going once, going twice. Click in. I got 1/2 times 4 times 0.6 squared plus 1/2 times 6 times 1.4 squared. So that one was 0.72 joules plus, yeah, so there you go, 5.88 joules. And I got exactly 6.6 joules. So that's an elastic collision. So good. Okay, discussion board, yes.
In elastic collisions, do the two objects always change direction?
I don't think so. I think if one has, even in an elastic collision, if you put a bunch of mass on one of them, it can continue going in the same direction. So, yeah, so no, that's the short answer to that. Yep, next question.
In totally inelastic collisions, is momentum conserved?
Yes. Momentum is always conserved in any collision or any explosion, so both good questions.
All right, final question.
Yeah.
When we are determining if a collision is elastic or inelastic, why were we comparing the momentum of the system before and after instead of their kinetic energies?
Yeah, that's a great question. So yeah, all you really have to do is compare the initial and kinetic energies if you know whether it's like real data or something. I guess with this one, I just as a personal, I guess complete practice, I like to check the momentum as same before and after. But you're right, it's really just the kinetic energy that determines whether it's elastic or inelastic. We're good? These are great questions, so thanks for typing those in. Thanks to Jason for. Okay, I want to do another example. This is from a previous test, but let's read it first. And I won't do this as learning catalytics, let's just work it out. Two cars, both of mass m, collide and stick together. Prior to the collision, one car had been traveling north at a speed 2v, while the second was traveling east at a speed v. So this is a two-dimensional collision question. Neglect horizontal forces in cars, such as friction from the road on the cars. Immediately after the collision, what is the speed of the joined cars? So the implication there is that it's a totally inelastic collision. And the next question is, what is the ratio kf divided by ki of the final to initial kinetic energy of the system just before and just after the collision? This is all the kind of stuff that we've been doing. You're doing impulse approximation, so you're neglecting impulse, external impulse. You're doing, it's stuck together, so that's totally inelastic. So let's just work it out. I've done it somewhere here. My notes are all the hell over the place here. Here we are. So, just trying to draw it here, I've got a mass m that's traveling east at speed v. So let's define y is north, and plus y is north, and plus x is east, just to keep track of things. And then another mass, same mass car, is going north with 2v. And it's joined. This means totally inelastic. This happens a lot, meaning that they're guaranteed to have the same final velocity because they're stuck together. And then so I would say that the final mass is 2m, whatever the kind of stuck together thing is of the two cars. That's some v, this question mark. So P initial x equals P final x. So P initial x is going to just be m times v. And P final x is going to be 2m times v final x. So what that means is that v final x is equal to v over 2. The m's cancel there, and you can solve out for just the x component of that speed. And then y component, I guess this seems to be much more of a chapter 6 question, which is that the initial, you're going to have that mass m car traveling north at 2v, and then finally 2m times v final y. And that means that v final y, the 2's cancel there as well, is just equal to v. So v final is equal to the square root of v final x squared plus v final y squared. You're just doing Pythagoras. Pull out the v, you get 1/2 squared plus 1 squared. It's equal to v times the square root of 1/4. Do a common denominator, 4 quarters, I guess. It's v times the square root of 5 over 4. So square root of 5 over 2 is e. I can hear a pin dropping here. Next question was to compare the initial and final kinetic energies. This is more like a chapter 7 kind of question. So we have to refer to that. But basically, K initial is going to come, it's going to be 1/2 m times v squared. That's the east-going car, plus 1/2 m times 2v squared. That's the north-going car. You can pull out the mv squared times 1/2 plus 4/2. It's going to be 1 plus 4, so it's mv squared times 5 divided by 2. Okay, and then K final is going to be 1/2 times 2m times v final squared. So, and we kind of worked at it last time, it's mv squared times 5 over 4. Just remember from before, you had v final is v times the square root of 5 over 4. When you square that, you get v squared times 5 over 4. Square root goes away. And so I would just do k, you're asked for k final divided by k initial is equal to mv squared times 5/4 divided by mv squared times 5/2. So you get 5 over 4 times 2 over 5, and you get 2/4. B. Okay. Turn this in here. Ooh, I want to do the basketball one. Well, yep, question, yes. Slide before? This was the one with just the In which question? Yep. So I just plugged in all of the values. So this was v final x is v over 2 squared plus v squared. So there was a v squared over 4 and a v squared here. So I pulled out the square root of v squared and got the v. Kind of skipped a couple of steps there. Okay? Yeah, it's good to check my algebra on these things. Well, like what I'm going to do next is we're going to keep it a little more conceptual than actually go through it. But basic idea with an elastic collision is that there is a way of actually solving what the final velocities of both objects is. So, you consider a head-on perfectly elastic collision, so an elastic collision of a ball of mass m1 with a ball of mass m2 that's initially at rest. And what's nice about this analysis is that you can always switch to the rest frame of ball 2, so you can always make the ball 2 at rest. Got some kinetic energy. During the collision, there's some stored kinetic energy, I guess, as the things compress or whatever, but then after, the final kinetic energy is the same. That's why it's elastic. And you can solve out for V1 final and V2 final. And by doing, you've got two equations and two unknowns, basically. Those are your two equations, and your two unknowns are the two velocities of the two different balls. You're assuming all of this is head-on, meaning it's all in one dimension. So it doesn't ricochet off like in pool. So, and this is the answer. I'll just say that these might be, I'll post this, but they're good equations to have on an aid sheet. Because they're a little hard to derive. When I was taking first year physics, they taught us, we went through really in detail how to solve this. It takes about maybe a page of algebra to go from these equations to these equations. But rather than do that every time on a test, I just used to write these ones on the aid sheet. Okay. And these two equations come in especially handy because you can always switch to an inertial reference frame in which ball 2 is initially at rest. So I want to do a little demonstration and then probably go through the math of it next time. But I want to balance a tennis ball on top of a basketball. So a basketball, again, is about 10 times the mass of a tennis ball, and drop them from rest at some height above the floor. And so what will happen is that there'll be a whole bunch of things will happen. Now let's split it up. And let's imagine that there's a tiny little air gap in between them. So the first thing that'll happen is that they'll drop. And they'll pick up a bunch of speed together. Because they both travel that same 0.82 meters. Then, what'll happen is the basketball will bounce. That's the second thing. And we might assume like an elastic collision with the floor, meaning that the kinetic energy of the ball is the same before and after. And it reverses its momentum, actually. Okay. Third thing that happens is that the basketball will almost immediately hit the tennis ball. And that could also be an elastic collision. And then fourth thing that will happen is that they'll both travel up until they get to zero final velocity. Want to try it? Takes a steady hand to kind of do this, but okay. That's another one of these party tricks that you can do at your next physics party. But okay, so idea being, okay, you can assume all perfectly elastic collisions. Segment 1, free fall. So just they both travel down. Segment 2, I would always do the basketball first. An elastic collision with the floor. So remember how I told you that momentum is always conserved in an elastic collision? Well, that doesn't count if you use the floor or a wall or something big that's attached to the earth. Okay? Because what happens is that the earth completely reverses the momentum of the basketball, but does conserve its kinetic energy. So Momentum is conserved in collisions unless it's colliding with something that's attached to the Earth. Okay. So then, in segment 3, there's this next collision which does conserve momentum and kinetic energy between the ball and the tennis ball, because the floor is not involved in that collision. And then segment 4 is they go up. So I can kind of just say that just before they hit the floor, if they fall a distance 0.82 meters, I can use my conservation of energy, I guess. Or I could use kinematics, whatever. You're going to get that equation you always get, right? Which is V final equals square root of 2GH. And it's going down. Anyway, they're both going down. Then all of a sudden, the basketball is then going up with 4 meters per second, assuming that it doesn't lose any energy during the bounce. So it's a sort of an approximation there. And then they collide. So then what you want to do, and I'm not going to do this right now, is you have to find the speed of the tennis ball immediately after the collision. So this could be a little maybe question we might do. You got a 0.5 kilogram basketball, which is moving upwards at 4 meters per second, strikes a 0.05 kilogram tennis ball, initially moving downwards at 4 meters per second. Their collisions are perfectly elastic. What is the speed of the tennis ball immediately after the collision? So my first step is going to be to switch to the reference frame of the tennis ball, so it's at rest. Second step will be to use these equations, just find out what their final velocities are in that reference frame. And then third step will be to switch back to the lab frame. Now, I promise I'll do that on Monday. You get 10.5. That's what, and then, so that's why, even though the basketball is going up with 4, the tennis ball ends up with 10.5 meters per second, so it flies really high up. 5.6 meters. So, have a great weekend. Hope you go to a party or something. We're going to finish chapter 7 on Monday. And don't forget, the term test is going to include chapter 8. So that's on November 15th. It's a few weeks away. And next week in practicals, you'll be doing a warm-up test on that stuff. So good luck on that. Cheers.